In this presentation, we'll be discussing the differences in beneficiation of magnetite versus hematite ores. Our content includes a bit on iron ore geology, the typical iron ore minerals and their respective magnetic susceptibilities. But then we have to take a step back and understand magnetism a bit better so that we can explain why different iron ore minerals have different magnetic susceptibilities. And then ultimately, how do we benefit from these different magnetic susceptibilities by understanding the magnetic force equation? We then have to look at the magnetic circuit design and what is within the control of the MagSep original equipment manufacturer. And finally, an indication of capital and operational cost comparisons for the two different beneficiation trains of magnetite and hematite. A bit on geology. Natural occurring pure hematite or pure magnetite is absolutely scarce. The iron ore cycle indicated on the right, as well as relatively easy weather requirements for iron ore, results in a magnitude of different minerals ranging from hematite through limonite, goethite, maghemite, up to the ultimate weathered form of magnetite. Over and above these different minerals that are present in an ore body, a lot of them could also have different thermodynamic states or pseudomorphic states within a single ore body. So one iron ore might actually contain a lot of different type of iron ore minerals. These varying minerals have varying magnetism and poses a challenge to physical beneficiation through magnetic properties. To quantify the magnetic susceptibility, we first compare the magnetic susceptibility of iron steel. So this is not a mineral, this is iron ore that's gone through all the furnaces and through a milling process. This is iron steel, a piece of iron metal. So we can see that it's 100% iron and that the magnetic susceptibility of this material at a volumetric SI unit has a value of 3.0. Magnetite with chemical formula that we've seen before today, Fe3O4, has just over 72% elemental iron in its structure and has a susceptibility of 2.7. In other words, it's only 10% less magnetic than pure iron. Hematite, goethite, and limonite, however, have much lower magnetic susceptibilities, also possibly associated to their iron ore percentage, but we will explain the link between the percentage iron ore and the magnetism in 2 slides to come. We can conclude from here that magnetite is 52 times more magnetic than hematite, but what does that all mean? So to understand that, we first have to understand where magnetism comes from. Magnetism results when the electrons in the outermost orbital shell of an atom are spinning in the same direction. In other words, these consecutive atoms must have the electron in their outermost orbital shell spinning in the same direction. Once their electron spin aligns, those atoms may become magnetic. Now we know that not all materials or minerals or elements can be magnetized, and that has to do with the presence and the distance of the electrons in the outermost valence shell from the nucleus. Some materials may turn out to be ferromagnetic, and they will offer a strong alignment with the magnetic field, and once that external magnetic field is removed, they would have prolonged magnetism. In other words, these materials have been magnetized and contains a residual, not 100%, but a residual magnetism on them, which then prolongs over time. Paramagnetic minerals have a random alignment of these electrons, and we have to excite those electrons into a different orbital band using strong magnetic fields, and once we remove the external magnetic fields, the electrons will fall back into their normal orbital shells and they would not be magnetic anymore. Finally, we get anti-ferromagnetic man-made material that does not get attracted by magnets, but actually repels away from the influence of externally applied magnetic fields. So how do we couple the different iron ore minerals with this phenomenon of aligned electron spin in an atom's most orbital valency? If we first consider iron steel, the charge balance in iron steel is a sea of electrons that are loosely associated with the nuclei. And because these electrons are loosely associated with the nuclei, it means that they are further from their nuclear distance, and they're not necessarily associated to a single proton or nucleus, but rather to multiple. And that is why we can manipulate the electron spin directions of iron steel by applying an external magnetic field quite easily, and why the magnetic susceptibility of iron steel is high at a value of 3. With magnetite, it becomes a little more complex. So the chemical formula for magnetite contains 3 iron cations and oxygen anions. The charge balance on the oxygen is 4 times a valency of -2 and results in a valency of -8. Now we know that the combination of positively charged iron cations must add up to +8 in order for us to achieve our charge balance. So we would have 2 Fe3+ cations that leads to a total charge of +6, and 1 Fe2+ cation that leads to a total charge of +2. And this cation, the Fe2+, is the important one that makes magnetite much more magnetic than hematite. Why? The Fe2+ valency means that we have an additional electron over the Fe3+ cation. That one additional electron is unpaired and sits in its own orbital shell, and it is also further away from the nucleus. So because it is unpaired, it is easier to influence the spin direction of that electron through an externally applied magnetic field. And because it's further away from the nucleus, again, there's not such a strong charge hold from the core of the atom onto that electron, allowing it to be magnetized. Hematite, however, has only 2 Fe3+ electrons, Fe3+ cations, which mean we do not have that extra electron we had in the Fe2+, making it only paramagnetic. So how do we exploit these magnetic properties of minerals? Well, if we apply a magnet to exert an attraction force F1 onto ferromagnetic particles in green, the force experienced by the particle will be larger than the force experienced by the same magnet, but on a paramagnetic particle. Non-ferromagnetic material, of course, would repel away from the magnet. In the force balance then, between the magnetic attraction force to the one side and the hydrodynamic or centrifugal and or gravitational forces acting on the particles through the magnetic separator, would result in a different magnitude of force balance between ferro-paramagnetic materials. We can then exert that force balance as engineers to achieve a certain property. With having particles experiencing more attraction force means that we would recover the ferromagnetic particles, but that we could have the paramagnetic particles being washed out of the magnetic separator. In order to quantify that effect, we must look at the magnetic force equation that says the magnetic force experienced by a particle is equal to, first of all, the susceptibility of the material. Next up is the volume of that particle, because the volume of the particle denotes the number of flux lines from our magnetic field that would penetrate the particle. In other words, the larger a particle is, the more flux lines would act on it, and the higher the magnetic force would be. And then finally, we have our magnetic field strength multiplied with the gradient of the magnetic field. So magnetic field in physics can be called flux density, and the last term in the equation, therefore, flux density gradient. So if we consider a fixed magnetic field and a fixed gradient, and also a fixed particle volume, and we only consider that the susceptibility between magnetite and hematite is different, it means that a magnetite particle would experience a 50 times stronger magnetic attraction force compared to a hematite particle. Now, this can be a friend or a foe depending on how we design our circuit. For example, if we want to remove tramp metal from a conveyor belt that also contains magnetite, the tramp metal, iron steel with a susceptibility of 3 and the magnetic susceptibility of the magnetite 2.7 is quite close to each other, which means if we want to remove tramp metal roughly the size, looking at the second term, the volume in our magnetic force equation, roughly the same size as our ore, we may end up attracting both the tramp metal and the magnetite. Conversely, when we put magnetite into a WIMS machine that is typically used for hematite beneficiation, the magnetite would be attracted so strongly that it would be nearly impossible to wash that out under operational conditions, and we may in fact choke the matrix, which is the separation surface of the WIMS machine. So as a magnetic OEM, an original equipment manufacturer, what do we have control of when we have to design a purposeful magnetic circuit for a purposeful ore with its own unique susceptibility and volume? Well, we cannot influence the magnetic susceptibility. We have to beneficiate the iron ore minerals that are there in their grades that they are there, because that is why we are mining the ore after all. So we cannot influence the mineral composition or the geology, and therefore we cannot influence the magnetic susceptibility. Quite often, we can also not dictate the volume of the particles because they have to be milled down to a certain size in order to liberate them from our silica, sulfur, or phosphor contents before we enrich the iron and get rid of the gangue minerals. The only thing we really have control over is the magnetic strength of the magnetic circuit as well as the gradient of that magnetic circuit. The product of the two, the flux density and the flux density gradient, is called the force factor. So we know what we can influence as magnetic OEMs, but there's still some laws of physics that we have to comply with. The first one is that different magnetic materials or magnet sources will have different strengths. For example, barium ferrite is a commonly known ceramic magnet material used in the manufacturing of low-intensity magnetic separators, and the saturation capacity of that material is only around 2000 to 2200 Gauss. If we rather use rare earth magnets, then the saturation capacity of the rare earth magnet material, which is completely different to barium ferrite in both alloy composition and price, the saturation capacity of rare earth magnets is 7000 Gauss. Finally, we can use electromagnetic coils and we can design them to have different strengths going all the way up to 25,000 Gauss. The next part of physics we have to comply with is that the magnetic field intensity decreases as illustrated by this curve as we move away from the magnet surface. The rate or gradient at which the magnetic flux density decrease is called the magnetic field gradient, and that can also be manipulated in our magnetic circuit design. So we can use LIMS magnets of 2000 Gauss, MIMS magnets, which are medium intensity magnetic separators that goes up to 7000 Gauss, or high intensity magnetic separators that goes up to 25,000 Gauss using electromagnets. If we use LIMS magnets or MIMS magnets, which are permanent magnets in the form of metal alloy blocks, we may not always reach 2 or 7,000 Gauss depending on the thickness of the material we use. So we carefully have to design the number of magnetic blocks we insert into our magnet circuit to make sure we achieve the optimum strengths. When we play around with the spacing of the magnets, we will also influence the depth of the flux lines running between the north and south poles, and we can therefore influence the gradient. So on the right-hand side is an illustration of a low-intensity magnetic separator showing the magnetic field lines in green and also showing that we go from 2000 Gauss down to 0 over a distance of around 200 millimeters. At the bottom, we're looking at a modeling animation of a high-intensity magnetic separator with the matrix rods, the actual separation surfaces, going up as high as 20,000 Gauss. But in between those two matrix rods, we go from a north pole at 20,000 Gauss down to 0 and back to a south pole of 20,000 Gauss over a distance of 4 millimeters. In other words, in the middle is where we've gone from 20,000 Gauss down to 0, and that would be over a distance of 2 millimeters. Then we can calculate the force factors resulting from these different magnetic circuits. So first of all, for iron steel in a tramp movable metal application, we know that 700 Gauss is often, not always, but often quite sufficient. We also know that the magnetic field depth of a typical overbelt magnet is 300 millimeters. That then allows us to calculate the force factor, which is the Gauss 700 multiplied by the Gauss over the distance of dissipation, 700 over 350 millimeters. And we have a resultant 1.4 kilogauss squared per millimeter gradient from a typical overbelt magnet. For magnetite beneficiation, the result is 20 kilogauss squared per millimeter from a 2000 Gauss magnetic circuit. For the in-between minerals ranging between highly magnetic magnetite and paramagnetic hematite, we may have to use MIMS machine, medium intensity magseps at 245 kilogauss squared per millimeter. And finally, for hematite, we have to use high intensity magnetic separators that has a 10,000 Gauss magnetic strength divided by a dissipation distance of only 2 millimeters, resulting in 50,000 kilogauss squared per millimeter. So we can draw two conclusions from the calculation of this force factor. And the first one is that high intensity magnetic separators are 2,500 times stronger on the force factor than a low intensity magsep. But for the untrained eye, moving from a 2000 Gauss LIMS to a 10,000 Gauss HIMS would result in a factor of 5 times stronger. But actually the magnetic force experienced by the particle from the force factor is 2,500 times stronger. Conversely, we can say that if we have a high intensity magnetic separator with an electromagnet coil, but we don't run it at full capacity, only 2000 Gauss, the resulting force factor there is 2000 kilogauss squared per millimeter. So we're running it at 2000 Gauss, but because of the 2 millimeter magnetic gradient, it still results in a 2000 kilogauss squared per millimeter force factor, which is still 100 times stronger than the LIMS, even though both of them are running at 2000 Gauss. We then go on to a simplified block flow diagram for magnetite beneficiation using a wet, low-intensity drum magnetic separator. Our cobbing stage would increase our grades from 40 to 55, followed by some further milling for liberation through a rougher stage 55 to 60, and ultimately to reach a saleable grade of 65%, we would need 4 stages of low-intensity magnetic separator. If we consider a simplified block flow diagram for wet, high-intensity magnetic separators working on hematite, we would only need 3 WIMS machines to upgrade the same particle size distribution of ore from 40 to ultimately 65% Fe in this block flow diagram. And now for our case study cost analysis between the two technologies required for magnetite versus hematite beneficiation. The base case is the same for both, and it is a production tonnage of 30 tons per hour at 65% Fe. We've mentioned that the number of stages required for magnetite beneficiation is 4, and the number of stages required for WIMS beneficiation is 3. The estimated capital equipment price for 4 wet drum magnetic separators is around $130,000 US. The estimated price to produce 30 tons per hour of 65% Fe for 3 stages of WIMS is $660,000. The electrical cost, calculated at $0.2 per kilowatt hour. We know that limbs are exceptionally low on electrical power draw. We only need a geared motor to rotate the drum. So we would need 5 kilowatt hours, which is a total of $1 per hour electrical operational costs. Wet high-intensity magnetic separators also have rotating components, but we also need electromagnetic coils to power up and provide the magnetism. And these coils are quite energy intensive at 70 kilowatt hours, totaling $14 per hour to run. The mechanical costs of operation, so mechanical maintenance, is estimated at 2% of the capital equipment price per year. If we then take the total cost of ownership over 5 years, it is the cost of the capital equipment plus the operational costs, electrical and mechanical, and we can see that magnetite beneficiation with wet limbs is around $170,000 over 5 years, but that WIMS beneficiation is close to $1.2 million over 5 years. Our conclusions then is that pure mineral iron deposits do not practically exist. The magnetic susceptibility devil is in the detail and can vary by a factor of 50. You will need a completely different magnetic separation technology and circuit design to beneficiate magnetite versus hematite, and that the 5-year cost of ownership could be 7 times higher for hematite that uses WIMS machines. However, if we receive analytical results at an early stage of a project, we typically receive an XRF analysis that reports the amount of iron as Fe2O3, even though the mineral might not be hematite with chemical formula Fe2O3, it is only a basis of Fe2O3. So therefore, understanding your ore, taking a closer look at it, and taking a look at the suit and also the pseudomorphical state of the minerals that comprises that ore is absolutely critical if you want to get your project finances and the type of magnetic circuit required correct.